everybody, and welcome to Unit 5, Lesson 11, which is again all about optimization, but this video is just going to be about doing example problems to show you kind of how to work through optimization scenarios. So the learning target for today is I can interpret the meaning of a maximum and minimum in a specific context. So we're going to be finding maximums and minimums, but in the context of a scenario, and we're going to make sure that that context then is kind of part of how we give our answer. So we're going to interpret what that maximum or minimum means in that story. Here is a strategy that we're going to use for solving optimization problems. This is one of the most common applications in calculus. We are often asked to find things like the shortest distance between 2 points, or the largest area, or the maximum volume of a container, or the largest profit for a business. All of these scenarios involve finding the highest or the lowest that a function might go. So, in other words, a maximum or a minimum. The procedure is going to be this. First, we're going to draw a picture and label the unknown information with variables. It is very important that you draw a picture when possible because it's going to help you visualize how all of the different parts of the problem fit together, how all the different variables connect. Then we're going to write an equation for the quantity that you're trying to optimize. So a lot of times these problems will have two equations. It's important to know that you have an equation for the quantity you're trying to optimize, meaning if you want the largest area, make sure you have an area formula somewhere in your problem. If necessary, it's not always necessary, but if necessary, you're going to write a second equation that relates the information that you know about the two variables. So in problems where there's two variables, you often need to eliminate one of the variables using substitution. That means you're going to need a second equation, and that second equation will help you substitute so that you can get rid of one of the variables, which is the next step. You would, if necessary, substitute the equations so that you only have one variable. And last but not least, because we want to find a max or a min, you're going to find the derivative and you're going to set it equal to 0 in order to find the extreme values. So in other words, the maximums or the minimums of the function. Let's work through an example for the first example here that only requires one equation. So it says here the apartment rental company has 1,600 units available, of which 800 are currently rented for $300 per month. A market survey indicates that each $5 decrease in monthly rent will result in 20 new leases. How much rent should be charged to maximize revenue? Now, the first thing here is to figure out what exactly we're trying to maximize. In this problem, I'm not going to draw a picture because I'm not talking about a geometric shape or a figure that I'm building a fence or something like that. I'm really just talking about the idea of profit here. So there's no real visual. But I do need to know that I want to write an equation that will help me maximize revenue. So I'm going to need a revenue equation. Now, when I think about revenue, I think that we can always find revenue or the amount of money we're going to make by multiplying together the number of items in this case, apartments, times the amount that we make per item. One way I always compare this is to the idea of candy sales at school. So if you're going to sell candy and you know you're selling candy, you're selling 25 pieces of candy for $2 each. To figure out your revenue, you're going to do 25 times 2. How many did you sell times how much did you make per item? It's the same thing here. It's how many are we going to sell times how much money is there per item. Now, in this case, we know that the revenue is going to be equal to, I'm going to call this R, the number of items. Now it says here in this scenario, we already have 800 currently rented. So right now the number of items is 80. But for each decrease, we're going to have 20 new leases. So each time we drop the price, we're going to sell 20 more. That means that the number of items is going to be however many we have now, which is 800, plus 20 new items each time we drop the price. So I'm going to put an X here to represent the number of price drops. Now, the amount that we're charging in this problem right now is $300. But if we decrease that by $5 each time, then that means that the new price would be 300 minus 5. And again, the reason it's minus is because we're decreasing the price, X number of times. So this X is still going to be the number of price drops. So we're going to get 20 new customers each time, and we're going to subtract $5 each time. Now that's my revenue equation. Before I take the derivative, which is going to be the next step, I'm going to make sure that I only have one variable. Because this uses X and this uses X, there's only one variable here, so I'm not going to need a second equation. Also, before I take the derivative, I'm going to simplify this equation because I really don't want to use product rule if I don't have to. So my new revenue equation, if I kind of multiply this out, 800 times 300 would be 24 with 4 zeros. 800 times negative 5 would be minus 40 with 2 zeros, x. 20 times 300 would be plus 6 with 3 zeros, x. And then minus 5 times 20 is 100, x squared. If I simplify this by combining like terms, I get that my revenue is going to be 240,000 plus 2,000 x minus 100x squared. Once you have a simplified equation, then you can take the derivative. So I'm going to draw a line here because I want you guys to really understand that after this step, we're now working for the derivative equation. The derivative of this number would be 0. The derivative of 2000x would just be 2000. And the derivative of negative 100x squared would be negative 200x. And we're going to set that equal to 0 to find the maximums and minimums. Now, if I slide the 200 over, 2000 is equal to 200x, so x equals 10. In other words, we should drop the price 10 times. Now, this question says, how much rent should be charged? So it doesn't say how many times should you drop the price. It says how much rent should you charge? Well, right now we're charging $300 and we should drop the price by $5 10 times. So the new rent would be $300 minus $5 10 times, which would be 300 minus 50, which is $250 per month. That would be my new rent. Okay, now let's look at an example or a couple examples that require two equations. So problem number 2 here says an open top box is made by cutting congruent squares of side length x from the corners of a 54 centimeter by 30 centimeter sheet of paper and bending up the sides. How large should the squares be to make the box hold as much as possible? And what is the resulting maximum volume? Now, one thing to point out here is that we are trying to maximize the volume of this box. So something to keep in mind is that ultimately we want to have a volume equation. This is definitely an example where I would recommend drawing a picture. So we're going to make a box, and it says it's open top, which means there's no top to our box. We're just building kind of the frame, the bottom of the box, by cutting out squares from the corners of a piece of paper and folding them up. Here's what that looks like. We're going to start with a 30 centimeter by 54 centimeter piece of paper. Now, from each corner, we're going to cut out a square. And because these, and this is not the best drawing, but it should give you the right idea, because these are squares, each of these is the same size. So I can label them all with X because I don't know how big of a square to cut out. I just know that I'm cutting out the squares. Now, when I do that and I then fold up the sides of the paper, I'm going to have a 3-dimensional box that looks like this. Now the height of this box, because remember, you're taking the edges and you're folding them up, the height now is going to be x. The length of the box, so kind of this edge right here, is going to be the 54 centimeters that I started with, minus x here, and minus another x here. So the way that we would write that is 54 minus 2x. And the width of the box, or the depth of the box, is going to be the 30 centimeters that I started with, minus x here, and minus another x here. So it's going to be 30 minus 2x. Okay, now remember, we want to maximize the volume. So we need to write an equation for the volume of this box. The volume here is going to be length times width times height. So that's going to be 54 minus 2x times 30 minus 2x times another x. Now, it's also important to note that there are some restrictions on the size of x. Because we're cutting this out of a piece of paper, I can't just make x as big as I want. What you should notice here is that x is being subtracted twice. So from this longer side, the biggest size x that I could subtract would be 27, because 27 would get me halfway. If I was to cut a square of size 27 out, I would actually end up just slicing the paper completely in half. For this shorter side, the biggest x would be 15, because that would be halfway across this 30. So that's kind of the second equation we have here. X has to be less than 15. It also has to be less than 27. It's just that 15 is more restrictive, so we have to stay within the 15, because otherwise you're just not going to have enough paper to cut out anything bigger than a 15 centimeter square. Now, before I try to take the derivative and solve, I do think it would be a really good idea to simplify this equation. So I'm going to simplify by distributing. First, I'm going to multiply these first two parentheses together, then I'll multiply by x. 54 times 30, I'm going to get 162 with a 0 at the end. And then 54 times negative 2 is minus 108x. Negative 2 times 30 is negative 60x. Negative 2 times negative 2 is plus 4x squared. And this whole thing is times x. I can simplify this again. So I'm going to have 1,620x. I'm just distributing the x. Now negative 108 and negative 60 makes negative 168. And when I distribute that x, it's going to be x squared. 4x squared times x would be 4x cubed. So this is kind of my simplified volume equation. Now, in order to maximize the volume, I'm going to take the derivative. So I'm drawing a line here to kind of visually remind us that after this, we're working with the derivative. The derivative here would be 1620 minus, let's see, it'd be 336x plus 12x squared, and we're going to make that equal to 0. Because this is a quadratic equation, in order to solve this, we're going to probably either need to factor or find the zeros. Just for the sake of this example, I'm going to try factoring. Now, I happen to know that the number 12 goes into all of the numbers here. So if I start by factoring out the number 12, and I'm just going to switch the order a little bit while I do this and put the x squared first, minus 336 divided by 12 is, I believe, 28. Let me just double check that. Yes, it is 28x. And then plus 1620 divided by 12 is 135. Now, if you try to factor this quadratic, you're going to end up that it's not factorable. So at this point, when you see a quadratic, it might be worth using the quadratic formula. Now, the quadratic formula says that we would do negative b plus or minus the square root of b squared minus 4ac all over 2a. However, because of the way that this one works out, this I'm going to use a calculator for. And another strategy you could use would be to graph this and find the zeros. So I would have x squared minus 28x plus 135. I'm going to go to my window and set my x values to be between 0 and 15 because we know that our x should be between 0 and 15. And I'm going to go to my graph. I'm going to look for any zeros within that window, and it seems to happen one time. So I'm going to calculate my 0, which is going to be between 1, 2, 3, 4, 5, 6, and 7. So I'm going to even make it 5 and 7. And then it gives me that x would be 6.1897503. Now, in calculus, you're always going to want to round or truncate after 3 decimal places. So our final answer would be 6.189 centimeter squares. So that's the first part of my question is how large should the squares be to make the box hold as much as possible? They should be 6.189 centimeter squares. In order to find the resulting maximum volume, I'm just going to go ahead and plug that number into my original volume equation here. And when I do that, I'm going to type in parentheses 54 minus 2 times 6.189, and then parentheses 30 minus 2 times 6.189, and then times 6.189 again. And that's going to give me that the resulting maximum volume would be 4,539.402 centimeters cubed of volume. And that would be the second part of my answer. So this is an example where kind of the second equation you need is the restriction on x. You want to make sure that your x makes sense in the context of the problem. In this case, it helped me figure out that x has to be less than 15. Now, the second example we're going to do here should look pretty familiar. It's actually very similar to the first example we ever did, which was in a previous video. It says a rancher wants to construct a rectangular corral using 200 feet of fencing. The rancher decides to build this adjacent to a barn. That means that it shares a wall with the barn, so it's adjacent or next to the barn. What dimensions should the rancher use to construct the corral so that it will enclose the largest area possible? So we've got this barn, and we're going to go ahead and build a corral right next to that. So it's going to be a rectangle in shape. We just don't know how big to make that rectangle. Now we're going to need to know the dimensions that give us the largest possible area. So eventually we're going to need an area formula, and we're going to need to know the dimensions that got us there. I'm going to label the height of this rectangle, which is part of what I need for an area, as y, and the width of this rectangle as x. Now I know also that it says that we're using 200 feet of fencing, so that might be important in a second. The first step is going to be to write a formula for our area. Because we want the largest possible area, we need an equation for that. So the area here would be x times y. Now, as soon as I see that there are 2 variables in this equation, I know I'm going to need another equation because I can't take the derivative if there's 2 variables like that. So the next thing I want to think of is, what do I know here that can help me have another relationship between x and y? And the answer is the total amount of fencing is 200. In other words, if we take the x and we add that with the 2 y's that are part of the fencing, the total amount should be 200. What I'm going to do now is just solve for x. So to do that, I'm going to subtract 2y, and I get 200 minus 2y. And then I can take this and substitute it into my area formula to create a formula that only has one variable. So my new area formula would be 200 minus 2y times y. Now, before I take the derivative, I'm going to go ahead and distribute just to make my life a little bit easier. So I'm going to have 200y minus 2y squared. Now, I'm going to take the derivative next. I'm going to draw a line to remind myself that everything after this is working with the derivative. The derivative, area prime, would be 200 minus 4y equals 0. I would swing the 4y to the other side, so that becomes 200 equals 4y, which means y is going to be equal to 50, and in this case, we're measuring in feet. Now that means that we can find x by just substituting back into this equation right here. So 200 minus 2 times 50 is 100, gives me that x should be 100 feet. And if we use the dimensions where x is 100 and y is 50, we're going to get the largest area possible. All right, that is it for today. Thank you guys so much for watching, and I'll see you soon for some practice.